This lecture is going to be on 3 final exam problems. And the first one involves 3 points, P, Q, and R. And I'm simply asking you to do certain tasks with them. And we'll go through each of these one at a time. What is the distance from Q to the z-axis? So when you move 1 in the z direction, going from the origin, that's not going to take you off the z-axis. But then when you move 2 in the x direction and then minus 1 in the y direction, you're creating a right triangle where it's 2 by 1, and you want to know the hypotenuse to get the distance to the z-axis. So this is taking you 2 away in the x direction, and this is moving you 1 in the negative y direction. And so you're going to be off by, again, the hypotenuse of that right triangle, square root of 4 plus 1, or square root of 5, from the z-axis. So the z-axis is a distance square root of 5 from this point, or this point is a distance square root of 5 from the z-axis. So that's the answer to part A. For the next one, we want to calculate the vectors PQ and PR. Going from P to Q, we take the coordinates here minus the coordinates here. 2 minus 1 is 1. Negative 1 minus 1 is negative 2. 1 minus a negative 1 is 2. So that's giving me the vector 1, negative 2, 2. Going from P to R, we have 3 minus 1 is 2. 0 minus 1 is negative 1. Minus 3 minus a negative 1 is negative 2. So that gives me PQ and PR, and that finishes that part. What is the vector of length 2 with the same direction as PQ? So what we want to do for that is take the vector PQ, first make it a unit vector by dividing by the length of PQ, and then we'll have PQ over the length of PQ, and that will be a unit vector going in the direction of PQ. And then we want to multiply that by 2. And that will make it have length 2. So we take PQ, divide by its length, and multiply by 2. The length of PQ is 1 plus 4 plus 4, and then you take the square root of that. So that would be the square root of 9, or 3. So we have 2 over 3 times the vector PQ. So I've just written it like this, but this will be the answer then to this problem. This vector will have length 2, and it'll be going the same direction as PQ. The next problem asks for the area of triangle PQR. Now for this problem, there's going to be an easier way to do it, and you'll see that in a moment. But let me go ahead and pretend like we're trying to do this question in more generality, and we want to know how you would approach this problem of finding the area of PQR, that triangle. And the general approach, I mean, there's different ways to do it, but we've done it with projections before. But probably the easiest way is to take the cross product of PQ and PR, or 2 of the vectors here, using sides of the triangle. So here's PQ and here is PR. So I get PQ here and PR here. I'm going to take the cross product. Again, this is 4 minus a negative 2 gives me 6. Here we get negative 2 minus 4 will be negative 6. And we do minus that for the J component. So we get 6 there. And then we have negative 1 minus a negative 4. So it'll be negative 1 plus 4, or 3. So the vector 6, 6, 3 then is the vector that's a cross product of these two, and the length of that vector will give you not the area of this triangle, but it will give us the area of the parallelogram we get by using 2 sides of this triangle. So if we have a parallelogram where one side is PQ and the other side is PR, then corresponding to that, there'll be 2 other sides that are parallel to those. But the area of that parallelogram will be the length of this vector. So that's 36 plus 36 plus 9. 72 plus 9, or 81. We want the square root of that. That's 9, square root of 81. So 9 is the area of the parallelogram. The area of the triangle will be 1/2 that. So the area of the triangle is 9/2. The next part, we want to calculate the length of the projection of PQ onto PR. So let me remind you how to do that. We go ahead and take the absolute value of the dot product of PQ and PR, and we divide by the length of PR to get the length of this projection. So PQ dotted with PR is going to be 2 plus 2, that's 4, minus 4. So it's 0. The dot product of PQ and PR is 0. So since that dot product is 0, when we divide by the length, of course, we're going to get 0. So the projection then, the length of that projection is just 0. So I'll put a 0 here. And if you think of PR as being the bottom edge of this presentation, PQ being perpendicular to PR would make it like the left edge of the presentation. If you were to project then this PQ onto PR, you're just going to end up with a point. So what this is telling you that since PQ is perpendicular to PR, we're getting a point when we do the projection of PQ onto PR. And that point will have length 0. What is the height of triangle PQR from Q to the base PR? Well, again, this is a right triangle. PQ and PR are perpendicular. The right angle is at P. So we have the base PR here, and then the height's going to be PQ. So we just want the length of PQ, 1 plus 4 plus 4, 9, then take the square root. That's going to be 3. So 3 will be the height. Again, that's coming from the fact that this was a right triangle. We didn't need to use that it was a right triangle, so just to remind you how we would do this in a different situation, we have the area as 9/2. The area is 1/2 the base times the height. The base was this PR, so we could have taken the length of PR here, which is 3. And so we would have 9/2 is equal to 1/2 the base, which is 3, times the height. So the height would be 9/2 divided by 3/2, and that would also give you 3. So you could calculate the height that way as well. The next problem comes from another final exam. And we've done some problems already on video where I've gone through global max or min. So I wanted to make sure we had another one with local max or min. So here we're going to be given some points, and we want to know if these are locations of a local maximum, a local minimum, a saddle point, or not a critical point at all. So what we're going to do is what we do when we try to find critical points is we take the derivative of this function f with respect to x and with respect to y, and we want both of those derivatives to be 0. So the derivative of f with respect to x, we get 2xy minus the y squared here, plus the 3y. Derivative with respect to y, we get an x squared here, minus a 2xy, plus a 3x. So we have these two derivatives, the derivative with respect to x and derivative with respect to y. We want to know when they're both 0. The point of this problem is you don't need to figure out where these are 0 because I'm not asking you to find the critical points. What I'm asking you to do is determine whether these are critical points, and if they are, whether they're local max, local min, or saddle points. So you just want to check to see if both derivatives are 0 at these points. If both derivatives are 0, then they're critical points, and we have to determine if they're max, min, or saddle point. If both derivatives are not 0, then they're not critical points, and that will be our answer, that it's not a critical point. So you can see if I plug in 0, 0 for x and y, both of these are 0, so that's going to be a critical point. 0, 0 is going to be a critical point. What about 1 minus 1? We get minus 1 for the product of x and y, so this is minus 2. And then minus 1 squared will be 1, so minus another 1. This will be minus 3. Y is negative 1, so this will be minus 3. So we have negative 3 minus 3, that's negative 6. That is not 0. We don't even have to check this. Both of them need to be 0 in order to be a critical point. This one's not 0, so this is not a critical point. So that one's not going to be a critical point. Let's check the minus 1, 1 here. Again, the product is negative 1, so we have negative 2 here. Y squared will be 1, so this will be minus 1. So we have negative 3. Then y is 1, so we have plus 3. So negative 3 plus 3 is 0, and this is 0. Let's make sure f sub y is 0. We have 1. This will be plus 2. So 1 plus 2 is 3. X was negative 1, so this is minus 3. We'll have 3 minus 3, that is 0. So this is also 0 at this point. So this will be a critical point, and this will be a critical point just because they're both 0 at both f sub x and f sub y. Okay, so we have our 2 points that now we need to determine if they're locations for a local maximum or local minimum or a saddle point. To do that, we use the second derivative test. The second derivative test says to take the second derivative of f with respect to x and the second derivative of f with respect to y, and then mixed partial here, the f sub xy squared. And we want to take, minus that. So we want to compute this. So derivative of this with respect to x, we're going to have 2y, and these will be 0. So 2y. Derivative of this with respect to y, we'll have 0 there. We'll have a minus 2x here and a 0 there. So minus 2x. And then the derivative of this with respect to y will be 2x minus 2y plus 3. And we want to square that. So this is d. Now we want to know what happens to d at each of these points. So we're going to plug them in. If I plug in 0, 0, I'm going to get 0, 0. I'm just going to have minus 9 here, minus 3 squared. So we're going to have d is minus 9, and that's less than 0. So that means we're going to have a saddle point at 0, 0. Let's plug in minus 1, 1. So this is 1 times 2, so that's 2. And this is minus 1 times minus 2, that's 2. So we get 2 times 2. Here we're going to have minus 2, minus 2. So minus 4 plus 3, that's minus 1, or negative 1 squared. So that'll be 1. So we're going to have 2 times 2 minus 1. And that's going to give you 3, which is greater than 0. And then since the derivatives, the second derivative with respect to x and the second derivative with respect to y are both positive, that means the graph of this function is going to be concaved up at minus 1, 1. And so we're going to have a local minimum at this point, minus 1, 1. So to summarize, the 1 minus 1 was not a critical point. The 0, 0 was a location of a saddle point. And the negative 1, 1 was a location of a local minimum. And remember, if I ask you for the local minimum value, you want to plug in this point into here to figure out what the value is. I don't usually do that with locals, but for globals, I certainly might. With the global minimum or global maximum value, you plug in the point you know where it occurs at and find the actual value of your function. Now I'm going to do an unusual problem. There's this person named Jacob Jingleheimer Schmidt, who was a high school buddy of yours, but you might not remember him. And he comes to you and he tells you that this curve here, where t is going between 0 and 2 pi, lies on some plane, but he can't figure out what that plane is. So he's asking for your help. He wants to know what the equation of that plane is. And you are to determine the equation of the plane and put it in the form that we usually write planes in, ax plus by plus cz equals some number d. And the question is, what are a, b, c, and d here? So it's tempting to try to figure out what plane this is by trying to figure out why this is on a plane. The question is telling you that this curve is on a plane. You don't have to show that. And this was a parenthetical comment that was also with this problem. That really all I'm interested in is you assuming that the knowledge that this is on a plane and finding out what plane that is. So the question is just to figure out what the plane is that this curve is on. And the way we're going to do that is we're going to go ahead and just find 3 points. And that sounds reasonable. If we just know 3 points on this curve is on the plane, then these 3 points will be on the plane. And then we can say what the plane is if we know 3 points on the plane. we have to be a little bit careful. I'm going to plug in t equals 0. I'm going to plug in t equals pi halves to keep these simple. And so the next thing to try is perhaps t equals pi. So we get these 3 points. And then this problem, rather than having all these words, is simply find the equation of the plane which passes through these 3 points. So we want to find the equation of the plane that passes through the 3 points I find by plugging in 3 values of t. This one looks a little strange. We'll get to that. So plug in t equals 0. We get minus 2 plus 3. That's going to be 1. Plug in t equals 0. That means this is a 1. So we get minus 3. Plug in t equals 0. We get 1 minus 2. That's negative 1. This point is coming from taking t equal to 0. It gives me a point on the curve, and so it's a point on my plane. Plug in t equals pi halves. Cosine is 0, so is cosine of 3 pi halves. So this is just going to be 3, 0, minus 2. And last, well, if I plug in t equals pi, this is negative 1 cubed. It's negative 1. We'll have 2 plus 3. This will be 5. Well, this is not what you get when t equals pi. So why did I do this? Well, if you plug in t equals pi, you get 5 here again. You get 3 pi here. Cosine will be negative 1. So you get 3 here. And here you'll get negative 3. So you'll get 5, 3, negative 3. You should try that and see what happens when you use 5, 3, negative 3 here. For the rest of the problem, go ahead and do the whole problem with 5, 3, negative 3 here. And you'll see why it doesn't work and how you would notice that it doesn't work. But I can tell you why it doesn't work now. But again, if you actually try this, you'll see what would happen if you were doing the problem and started to do it wrong. You would realize that it didn't work. Okay, so what is bad about taking t equal to pi? Well, you can't tell this immediately from what I've written up here, but these 3 points, if you take t equals pi, would be collinear. They'd be on the same line. And if you think about having 3 points on the same line, there's not a unique plane that passes through those 3 points. There's more than one plane. There's definitely many. So we don't want to have 3 points and say we can figure out the plane from that, because it's not true. There's infinitely many planes that would pass through those 3 points. So we need 3 points that are not all on the same line, 3 non-collinear points. And then if we have 3 non-collinear points, then there's only going to be one plane that passes through the 3 of them, and we can try to figure out what that plane is. So what I did here to get a different point, since taking t equals pi didn't work, is I took t equals pi thirds, because at least then I know cosine's a half. It's something simple and not too messy. So if I take t equals to pi thirds, the cosine of pi thirds will be 1/2. This will be 1/8 when I cube it, times a minus 2 will give me minus 1/4, plus the 3 will give me 11/4. If I plug in pi thirds here, then I'll have cosine of pi, which is negative 1, and this will become 3. Pi thirds here, I get again 1/2. 1/2 minus 2 is minus 3/2. So this point is coming from taking t equal to pi thirds again. So we have 3 points that are now, well, we'll see if they're not collinear, because again, it'll come up if we keep going. So how do we find the equation of the plane if we know 3 points on the plane, 3 non-collinear points? We take vectors using all 3 points, but one vector going from one to the other, and then use this point somehow. You can use this vector, or this vector, or this vector, or this vector. Just take 2 vectors from these 3 points, making sure you're using all 3 points. So I'm going to take this vector and this vector. So u is a vector going from this point to this point. We have 2, 3, minus 2 minus negative 1 will be minus 1. So 2, 3, negative 1 is the vector from here to here. And then I'm going to take the vector from this point to this point. That'll give me 11/4 minus 1, which is a 7/4. A 3 minus a negative 3 will give me 6. A negative 3/2 minus a negative 1 will give me negative 3/2 plus 1, so negative 1/2. So these are my vectors u and v. They're parallel to the plane because they came from taking points on the plane and going from one point on a plane to another point on the plane. So these vectors are parallel to the plane. We take their cross product and we're going to get a normal then to these vectors and hence a normal to the plane. You can see these vectors aren't multiples of each other. If I want to multiply this times something to get this, I would have to make it a 2 in order to get a 6 for the second component. But then I would need to multiply by 2 here, and that's not giving me 7/4. So it's not true that something times this is going to equal this. So that means that these 3 points are non-collinear. So what we want to do again is take the cross product. The cross product of u and v will give me a vector that's normal or perpendicular to these two vectors. So 2, 3 minus 1, 7/4, 6 minus 1/2 for the two vectors. And when I take the cross product, I get minus 3 halves plus 6. So minus 3 halves plus 12 halves, or 9 halves. Here we have a minus 1 plus 7/4. Minus 1 plus 7/4 gives us 3/4. We want minus the j component, so minus 3/4. And then we have 12 minus 21/4. Well, 12 is 48/4, so it's 48 minus 21, all divided by 4, or 27/4. So this is the cross product. And again, this then will be perpendicular to the plane we want, normal to the plane, and we can use this as our normal to the plane. Now, it's a little messy, and it's easier to take out the 3 we have and actually the 4 in the denominator. So if I take out 3/4 here, notice this is what I'd get. This would be 18/4, or 9 halves. This would be minus 3/4, and this will be 27/4 when I multiply this out. So I just take in out a 3/4. And I get 6, negative 1, 9 for my vector here. And why does this make sense to use this vector? Well, these vectors are multiples of each other. If this is normal to my plane, this will also be normal to my plane. So this is a vector that's normal to the plane we want. And so I can use the 6, negative 1, and 9 for the coefficients of x, y, and z. So I get 6x minus y plus 9z. And then I get it equal to something, and I figure out what the something is by using that these points have to be on this plane. So I get 6 times 1 is 6, plus 3 is going to be 9, minus 9 is 0. So if I plug in 1, minus 3 for y, and minus 1 for z, I'm going to end up getting 0. The same thing here, I could have 18 for 6 times 3, 0 won't make any difference for y. We'll have minus 18 for 9 times z. That'll give us 0. You can also use this point, but it'll be a little bit messier. So 0 is the right constant there, and we see then that this plane equation has to be 6x minus y plus 9z equals 0. Okay, so that's the last problem I'm going to do for this lecture, and I will end the lecture here.